Hi everyone, my name is Thomas Kim. Today is May 11th, 2022. This is 108th episode for CUDA SQL OpenGL OpenCL MFC tutorial series. In our previous episode 107, Numerical Analysis 1, we learned how to implement Symmetric difference quotient derivative algorithm. In our previous episode, we learned numerical differentiation. If you double-click this link, you can watch episode 107, Numerical Analysis 1. In our previous episode, we learned how to determine polynomial functions. Click Show More. In the Download Source Code section, double-click this link. This is my English YouTube channel. In the section Linear Algebra and Algorithm, Linear Algebra and Threading Building Blocks in this series, if you scroll down, you can find episode 5, Numerical Differentiation 3. In this video, I explained mathematical reasoning behind 5-point stencil algorithm. Click Show More, download the source code. Right-click, Save Link As. Then Save. You will see this warning message, Keep. So, we basically downloaded two files, unzip it, also unzip it. From 5-point stencil, double-click it, copy, paste, in 107 symmetric derivative. Paste it here. Now, we will rename this folder. Rename 108 5.2 stencil. Copy the folder path. Copy. Paste it here. If you want to follow my current and future sessions, I assume you have watched these videos listed here. Otherwise, you may not be able to follow my current and future sessions. Now, start Visual Studio Code. Open SQL OpenGL OpenCL folder. From this folder, we will create a new file, derivative.co. Hit enter. For your reference, I will copy and paste these links. We also need to open Talk Play Fun CUDA extensions. We also need 5-point.cpp for our reference. Ctrl B. I will arrange side by side. Ctrl Home. In Talk Play Fun CUDA extensions.hpp, we need to define this macro here. We also need CMath here. Now, Ctrl End. Right before end of namespace, Talk Play Fun CUDA extensions here, we will define a function template, type name, func type name, arg, type name, delta, type, to underscore host, to underscore device, to underscore return type is arg type. Derivative 5-point stencil base. fun type f arg type x int n delta type h. This is our first implementation for 5-point stencil algorithm that supports both CPU device or GPU device or accelerators. That means I may modify this function anytime. I will use this code, copy, and paste it here. I will indent instead of keyword auto. I will use arg types. Then here arg type f1, we will call this function recursively. We pass f x minus 0.1 n minus 1 h. Copy, paste f2 x plus 0.1, then return f2 minus f1 over 2.0 times h. Please understand that in our previous episode, in this video, I explained symmetric difference quotient algorithm. We are using different quotient algorithm here. We also use recursion. We are calling this function recursively. Also, in this video, I explained in gory detail about 5-point stencil algorithm. With this, we will create one more function here, template, type name, fun type name, arg type name, delta type. We will set it arg type as default. I will just set it to double. Return type is arg type derivative 5-point stencil CPU fun type f arg type x int n1 first order derivative delta type h 0.0 f. I will set it float. Now return, we call this function like this, f x n h. We will test derivative 5-point stencil CPU in this file. Include quote period / Ctrl Z, include talkplay fun CUDA extensions. We will define namespace alias called TCE talkplay fun CUDA extensions. talkplay fun stream print auto and there talkplay fun and there void test 5-point stencil CPU int main. Copy this function name, paste it here. Auto F1, we are creating auto x, a lambda, return std sin x. Auto numerical dev, numerical derivative, TCE derivative 5-point stencil. We pass f1. f1 is this function. Then plot m phi 4 auto accurate derivative std cosine m phi 4. We will use plot. Please understand that f1 is std sine function. We are differentiating f1 or sine function at pi over 4. Auto difference std abs accurate derivative minus numerical derivative. This is the difference or error. Print I say sine prime x at x equals pi over 4 equals, the first comes numerical derivative, numerical, then comes accurate derivative, accurate, then comes difference. I will put a carriage return here, difference, and there. I will give a space here. Now we are calling this function. Sorry, I made a simple mistake here. It should be 1 and I will change it to double. Please take note. This is our version implementation. The first implementation for 5-point stencil algorithm. By version implementation, I mean I can change my implementation anytime. I changed it to forwarding reference. Also, I will change it to L-value reference. With these modifications, we start command prompt nvcc std C++17. This switch is must-have, compulsory. We also need extended lambda. We also need expt, relaxed context per. We also need ptx as minus suppress stack size warning. I will make this window bigger. Then derivative .cu or n.exe, hit enter. We built successfully. I will copy this command string here for your reference. In the command prompt, clsn. So This is numerical differentiation. This is accurate differentiation. This is the difference. Our 5-point stencil numerical algorithm gives correct result. 5-point stencil algorithm is very accurate. 5-point stencil derivative algorithm is known, famous for its accuracy and efficiency. Now, I will close this file, 5point.cpp, Control Home. I will copy this link, copy, and I will paste it here for your reference. Please understand that this code can be executed both in CPU and in GPU. In case of we are using recursion, here we are using recursive function call. In such case, we may need to define stack size of GPU device. So, if you haven't watched this video, CUDA tutorial 16 stack size and recursive function call in CUDA kernel, please control-click and watch this video. When we use recursive function call in the kernel, especially CUDA kernel, we sometimes need to manually set CUDA kernel's stack size. So you have to watch this video if you want to prevent stack overflow. In this case, we don't need to concern much about stack overflow. Now, here I will define a CUDA kernel like this. Template, type name, func type name, arg, type. Here, type name, return type name, delta type, to underscore global, return type is void, derivative 5-point stencil kernel, return type, this is pointer, r, func type, this is L value reference, arg type, x, int n, delta type, h. This is our function parameter. I will change or modify like this. I made a typo here. Now, int thread id block dim x times block index x plus thread index x. R, we take R as pointer here. Thread id equals, we call this function like this. Here we pass f, then x, then n, then h. This is our CUDA kernel. Here, template, type name, func type name, arg, type name, delta type. We are using GPU, so I will set it float as default type, arg type, derivative 5-point stencil GPU, func type. I will make it forwarding reference f, arg type x int n. I will set it 1. This is first order derivative by default. Then comes delta type h equals 0.01 f. Open curly brace. Auto device R. We allocate memory. malloc device. We pass arg type. We allocate device memory for a single instance of type arg type. Now we call this kernel. We will simply pass one block, one thread. Device R get. We need to pass pointer, then f, x, and h. We have to wait. CUDA device synchronize. arg type host R copy to host from device. We pass host R, then device R. Copy the value from device memory to host memory. Now return host R. So we implemented derivative 5-point stencil GPU with simple kernel invocation. In next episode, we will optimize this part of the algorithm. Now, Ctrl and copy this function, paste. Now, GPU, we change it to GPU. Copy this, paste it here, print using CPU. Copy this, paste it here. One more new line character. The condition is exactly the same. Now we rebuild. We have this error message. The closure type for lambda cannot be used as template type. I will copy this and paste it here for your reference. If you have such error message, then we have to host or device. In this case, device is good enough. Now we build again. 757 F undefined. 757 F. I made some trivial mistake. We rebuild. We built successfully. N. In this case, we are using host device. In this case, we are using GPU. In case of GPU, this is the difference. -6 power of 10. So, this algorithm is accurate up to 6 decimal point. 1, 2, 3, 4, 5. Accurate up to 5 decimal point. If we want to increase the precision, then we can change it to double, double, I will fix like this. Also here underscore 4. In this case, this is plot, this is plot. In this case, we are using double. Now let's try CLSN. Now it is accurate up to 10 to the negative 10. Or we can increase 1, 0.001. We will try this. CLSN. Now the accuracy improved significantly up to 10 to the negative 14th. This is GPU. In this episode, we implemented 5-point stencil algorithm for both GPU and CPU. We will further improve this algorithm in near future sessions.